Hey guys, in our previous lecture, we considered fixed law, and the reason we considered that was we are interested in partial differential equations and handling them. So we took one form of this PDE that was hugely relevant to us in the framework of material science and material research. So we considered it and we saw a way to solve it. Now, in this and in the subsequent lectures, we are going to look into something that is quite different. Now, let us begin by imagining two vectors. Let's say vector A and another vector B. Now, if I want to relate these two vectors, one possible way for me to do that will be maybe bring in my B vector to here, so that I have something like an A vector and that of a B vector. So I'm not compromising the magnitude or that of the direction of the B vector, although it might look like I have compromised, but still I'm moving my B vector to this origin point of A vector. Now I have the same origin for my A and B vector. Now essentially I can project my A onto B, B onto A, add it, subtract it, whatever I want to do, I can do with it. So this way I will be able to relate my A vectors and B vector. Now on the other hand, imagine that I have an A vector, let's say this one, an A vector, another vector B, and they exist in their own space. Yeah, so they exist in their own space. Yeah, of course there can be several mathematical meaning and several definitions that we can give to these spaces here. But let us for simplicity consider that these vectors mean different things in the physical world. So I have my vector A, I have my vector B, they exist in their different spaces, and what I mean by spaces in this context is they have their own physical meaning. On top of it, the coordinate system, the framework that defines the direction of this vector are oriented in different directions in both of these spaces. So in this case, I have this direction here, but it corresponds to my A space, and in this case my direction looks something like this. So both of these spaces are defined by three orthogonal unit vectors, and these three orthogonal unit vectors are pointed in different direction in these spaces. Now in vector A, or the space that pertains to vector A, the orthogonal unit vectors, let's assume it to be I, J and K. In this case, in vector B, let us assume that to be I prime, J prime and K prime. So two vectors, two different spaces, they are defined by their orthogonal set of bases. In A space we have I, J and K. In B space we have I prime, J prime and K prime. Now our goal is to rather relate our A vector to that of B vector. Now in order to do what we are going to do is we are going to come up with a new space that includes both this A space and B space. We are going to merge these two spaces and then come up with a new space. So this space, let's see, it looks like this. This is our new space. And what we have essentially done is, while creating this new space, we have rotated our coordinate systems of the B space in such a way that both A vector and B vector align on the same plane. They are equal. So we are merging two different spaces, creating a new space. When we are rotating the B vector or the B orthogonal basis in such a way that our A vector and B vector are equal. Our goal is to ensure that our A vector and our B vector, they superimpose one another. A and B vector superimpose one another. So vector A is equal to that of B in the new space that we have created. So it means, in addition to the magnitude, the direction of the B vector should be parallel to that of the A vector. In order to achieve that, I'm rotating the coordinate system that pertains to our B space. Now if I draw my coordinate system alone, my original I, J and K will look like this, something like this, I, J and K. And now since my I prime, J prime and K prime are rotated, it might look something like this. These are rotated planes. So these are my I prime, J prime and my K prime. So I have two vector spaces, I'm merging them to form a single space so that my A vector and B vector, they are equal, they superimpose over one another, and in order to achieve that, I'm rotating the space of B. And now I have two different frames of reference that have the same origin, that are superimposed on one another, but one is rotated with respect to another. So there is some angle using which we can relate these two different bases. Again, these two different bases, I vector, J vector and K vector, can be related to that of I prime, J prime, K prime through some angle. Right. Now, since my A vector and B vectors, they are now equal to one another in this new space, let us begin by defining what our A vectors and B vectors are. So, having understood this graphically, let us begin by describing what my A vectors and B vector are. Now, my A vector, I can write it as AI plus BJ plus CK. So this is my A vector that pertains to its A space. So my A space is it's constructed using orthogonal bases I, J and K. So therefore my A vector is written like this. My B vector, I can write it as A prime, I prime vector, B prime, J prime and C prime, K prime. So having graphically represented my A vector and B vector and their corresponding spaces, now we are writing it down. My A vector, it belongs to I, J, K space. So I'm writing it as AI, BJ and CK. My B vector, it belongs to I prime, B prime and K prime. So I'm writing it as A prime, I prime, A prime or B prime, J prime and C prime, K prime. Now, if I want to know how much of A vector can be found in the ith direction. So I'm considering a space that is described by I, J and K. I want to understand this A vector of mine, how much of this A vector is found in this I vector. All I need to do is take the dot product of A dot I. Again, I'm considering A vector and I want to know how much of the A vector is present in the I direction. So to know that, to quantify that, I'm taking the dot product of A vector and I vector. So this happens in the separate space. Now I can also do the same in the newly constituted space wherein I have both A and B. I can do the same in the newly constituted space wherein I have both A and B superimposed on one another. So I have my A vector superimposed on my B vector, and this is possible because I'm rotating my orthogonal basis. Now I can do the same when I take the dot product of A vector onto the I vector in this new space. I will be able to find what is the component of A that is found in the B direction or in the I direction. So what I'm doing is I'm taking the dot product of A vector to that of I vector. Now in this new space, I've constructed the new space. I've introduced my B space into the new space in such a way that my A vector is equal to that of the B vector. So this means my dot product of A vector dot I vector, which should be equal to my A. So if I take A vector here and take its dot product with respect to I vector, I will find that only this term survives, this term survives, the first term survives, and all the rest of the term vanishes. The reason rest of the term vanishes because when I consider the product, the first term gives me I dot I, the first term gives me I dot I, the second term gives me I dot J, and the third term gives me I dot K. And because these are orthogonal bases, I'm going to end up with cos 90 here and a cos 90 here. So that means these two guys are going to vanish off. So when I take the dot product of A vector and my I vector, I'm going to end up with A. Now I'm considering this dot product in this new space, and in this new space my A vector is equal to that of my B vector. So essentially what it means is A prime I prime vector plus B prime J prime vector C prime K prime vector, the dot product of this vector is equal to A. So since I'm doing this projection, this dot product in the new space, this new space wherein my A vector is equal to that of my B vector, I end up having this expression here. Now, when I expand this term, what I would end up getting is, so I have A prime I prime vector, B prime J prime vector, C prime K prime vector dot I vector is equal to my A. If I expand this, what I would end up getting is A prime I prime vector dot I vector, B prime J prime vector dot I vector plus C prime K prime vector dot I vector is equal to my A. So ultimately what I would end up getting is A prime I prime vector dot I vector, B prime J prime vector dot I vector, C prime K prime vector dot I vector. So what essentially we have done is we have treated the dot product of I vector with respect to these individual terms. So A prime I prime vector dot I vector, A B prime J prime vector dot I vector, and C prime I prime vector dot K prime C prime K prime vector dot I vector. So that is again equal to A. Now I can do the same for my other bases as well, meaning I can take the dot product of A vector dot J vector, which will give me my B, and this would essentially lend me. So initially I took the dot product of A vector and I vector, that gave me A, and this ended up giving me this relation here. I can do the same for A vector dot J vector, which will give me B, and if I replace my A vector with B vector because I'm considering such a space, then that would give me a relation wherein A prime I prime vector dot J vector plus B prime J prime vector dot J vector plus C prime K prime vector dot J vector is B. Now also I can take the dot product of A prime or A vector to that of my K vector, which will give me C, which will then be equal to A prime I prime vector dot K vector, B prime J prime vector dot K vector, C prime K prime vector dot K vector, which is equal to C. So I have three relations that have A, B, C on the right hand side, A prime, B prime, C prime on the left hand side. So A, B, C, they pertain to our original A vector, A prime, B prime, C prime, that pertain to our B vector. So these were originally defined in their own spaces. We have come up with a new space, and when we have this new space, and when we have manipulated B in such a way that both A and B vectors are equal, so essentially we are now able to relate the components of the A vector to that of the components of the B vector. Now this, I can rewrite it in the matrix form wherein my A, B and C assume a columnar matrix, and the components, these components here, they can be expressed as a 3 cross 3 matrix. These components here, they can be expressed as a 3 cross 3 matrix. These dot products here, they can be expressed as a 3 cross 3 matrix. So I'm taking my RHS and expressing it as my column matrix, and on each of these equations I have A prime, B prime, C prime. So those as well I can write it as a column matrix. So A prime, B prime, C prime. So all these three equations here that relate the components of my original A vector to that of the original B vector, the components, the original A and capital B, these vectors, these three expressions that relate these two original vectors, I'm writing it in the form of a matrix. So my components A, B and C that pertain to my A vector, they form a column matrix. A prime, B prime and C prime, that are the components, the scalar values of my B vector, they form another column matrix. Now the square matrix that relates these two, I'm writing it by just considering the dot products. So in this case I will have I vector dot I vector or I prime vector dot I vector, j prime vector dot I vector, k prime vector dot I vector. Now in this case I will have I prime vector dot j vector, j prime vector dot j vector, k prime vector dot j vector. In this case I will have I prime vector dot k vector, I or j prime vector dot k vector, and k prime vector dot k vector. So all these components here, the dot product components or these dot product terms, they assume their places in the square matrix. So A, B, C, A prime, B prime, C prime, they form the column matrix. All the rest of the term, they assume their positions in the square matrix. Now when you consider these individual terms, let's take one of these terms. When you consider these individual terms, I dot I prime, if you consider this term, ultimately this term will be equal to 1 dot cos of theta I prime. So these are two unit vectors. I'm taking the dot product of it. So it's going to be 1 cos theta I prime. So essentially it's going to be cos of theta I prime. So this matrix here, then we can write it as theta I prime, or theta, let's say, to make it simpler and rather consistent with what we have been doing, yeah, it will be I prime j, and I prime k. Not really, forgive me. So it's going to be I prime I, j prime I, and theta k prime I. And the other one, it's going to be I prime j, j prime j, and theta k prime j. And this is going to be I prime k, j prime k, and this is going to be k prime k. So I have rewritten this matrix, the matrix that constituted the dot products, using the thetas that relate these different bases. So essentially what these theta mean is, when I have such a combined frame of reference like I and j and k, on which the I prime, j prime, and k prime are superimposed, my theta I prime I, it corresponds to this angle here. My theta j prime I, it corresponds to this angle here, the theta j prime I. So essentially these thetas, they are the angle separating the corresponding orthogonal bases. So theta k prime I is the angle between the bases k prime and I. Theta I prime j is the angle between the I prime basis and j basis. So these are the angles that separate, or the angle between these corresponding bases. And using these angles, we are relating the component of the original B vector to that of the original A vectors. So essentially we have one vector existing in its own space, another vector existing in its own space. We are bringing these two vectors up, and we are forming a new space, and in this new space we are trying to relate these two vectors. And when we are trying to relate these two vectors, we ensure that in order to relate them, we ensure that these two vectors are equal. And when these two vectors are equal, and when we want to relate the components of these vectors, we have to use this matrix here that includes all the cos of the angles between them. So these are just not thetas, these are cos of the thetas. So these are cos of the thetas. Now of course, if you want to verify, we can very well see, I can take this product here, this product here, and this product here. This will give me my A. So I prime dot I of A prime will plus j prime dot I and B prime, k prime dot I and C prime. The sum of all these is going to give me A. So this holds true, and as when I replace these dot products with that of the cos thetas, now essentially I'm able to relate the components of my A vector and the components of B vector in the newly formed space. Okay, the way we are able to relate it is in the newly formed space, we are ensuring that the A vector is superimposed and it's equal to that of my B vector, and this equivalence is rather achieved by cos of these thetas between them. So these are often called as direction cosine matrix, but at this point it is rather not so relevant, because this is what gave birth to tensors. So the whole concept of tensor, the foundation, the origin story of tensor lies here, because when we consider A vector and A vector in its own space, we said that this own space, apart from having its own mathematical description, we can give a physical meaning to it. Now I can give a physical meaning to this own space as, let's say, load. So when we built our A vector in its own space, we said that this own space has its own mathematical description. For my ease of my understanding, I attribute a physical meaning to it, and this own space now I can refer to it as load. And in the same way, this B vector and its own space, I can refer to it as area. Now of course you can question, how can an area be a vector? Now imagine that this area is tangential to a specific direction, so this direction indicates the orientation of this area. So if I have a cube like this, or if I have a structure like this, this area need not always be equal to this area here. So in order to describe this inclined area, I introduce a vector, and this vector is tangential to this area, and I describe my area using this vector. So my B vector is that of an area. So I have two spaces. One space I'm attributing it to load, the other space I'm attributing it to area. Now ultimately then, this matrix that relates or equates area to that of the load in the new space is what we refer to as the stress. So I have load, its own vector, I have area, its own vector. I'm considering it in the single framework, and the single framework, the way we are able to equate load and area in a single framework, the what relates the load and area in the single framework in a single space is the stress. Now as you can see, the stress depends not on one index, it's not a row matrix or a column matrix, it depends on two indices, and a quantity that depends on two indices more than so instead of just one index, say direction, the quantity that depends on two indices, that's where we start introducing the term tensor. Of course, in the subsequent lectures we will see how vector is also a tensor, but still this is how tensor was introduced in the framework of physics. So you have load, we have area, we have one vector, we have another vector, each operating in their own domain, each operating having their own physical significance. But now when we bring them together in a single framework, we are able to relate them through some other quantity that just is not dependent on one direction or one index, but depends on two indices, and this is what we refer to as tensor, and this is called as stress. Load by area, we might have heard, we call this as stress, and this is how the tensor was introduced in our scientific community. So with this understanding, we will wind up this session, and we will try to understand more about tensor in the subsequent lectures. Bye guys.